Support us by hitting the thumbs up button and subscribe to our YouTube channel.
Okay, good morning, everyone, and welcome to another episode of Liknayan podcast. Today, I'll be your host. This is Cherry, and today we will be joined by an astrophysicist, Miss Isabella Huckabee. How do you like to be called, Isabella?
Actually, professionally, they call me Izzy.
Izzy.
Professor freshman year called me Izzy once, and it just stuck. So you can call me Izzy.
Okay, so easy. So, do you mind giving us a brief background of what you do, or what your research is, or anything you want to share?
Yeah. So I mainly do research on, I would probably say, substellar objects. So, basically anything in between planet-sized and star-sized. Well, I guess I do stars as well, but like small stars. And then all the stuff in between can be called brown dwarfs. So I do research on orbits of them, as well as I've done atmospheric studies, or I've done atmospheric studies as well.
So when you say you're working on research with planets and brown dwarfs and stuff, it's more of detection or like atmospheric?
Both. So for exoplanets, the projects I've been involved with are more detection rather than characterization. And with brown dwarfs, it was more atmospheric characterization.
So how do you characterize, let's start with exoplanets. How do you do the detection of the exoplanets?
So when I interned at NASA, I worked on a project called Exoplanet Watch. And basically what we did is we mobilized or put together a community of amateur astronomers to detect exoplanets. And we do this through something called the transit method. So basically, if you know what a solar eclipse is, the moon blocks out the sun, things go dark. Same idea for an exoplanet transit, except on a much smaller scale. So when a planet, from our point of view, goes in front of its star, it's going to block out some of that starlight, and that will create a dip in the brightness of the star. We can measure that dip. And if we see a dip in the brightness of a star, periodically, so like, we happen to see a dip every 3 days. That's pretty interesting. I bet there's a planet there that's orbiting every 3 days. And so what we do is work with amateur astronomers to detect these dips and then analyze their data and upload that data back online.
So how do you differentiate if it's periodic? That's the time you say it's probably a planet and not just a passing, let's say, whatever thing would pass.
Yeah. I mean, here's the thing. It could totally be an alien spaceship. It could very well be like an alien spaceship. But based on prior information, based on what we know that there are planets in our solar system. And the data is consistent with something that could be a round object. So it's more probably going to be a planet. And also, I mean, it could, we do see variations in brightness with stellar flares as well. But stellar flares typically they leave a certain signature, and they leave other clues, like the emission lines. Versus a transit is just the blocking of the light. There's typically no emission lines that pop up as well.
So, for example, when a planet is blocking a part of, let's say, the star, so you're measuring the dip, and if it's consistent, that are you measuring? My image is that you're measuring the same amount of dip that would pass through. So if it's the same amount of dip, let's say for what you said, let's say every 3 days you're measuring the same amount of dip, that's the time you say, it's the same planet or something.
Yeah, exactly. Yeah, so there are times where we see dips that are of different sizes. So same star, but like, okay, for some reason every 3 days we're seeing a dip of like, medium size, but every 3 days we're seeing a dip of a really big size. But every 50 days, we're seeing a really small dip. So it could be that there's two planets, and we can differentiate their sizes based on the size of the dips.
So this is just like brightness detection. So it doesn't matter uh, how long out or which part of this star this particular planet is blocking. Like it could go all the way around in the middle or just a tiny portion on the edge.
So typically, it needs to be pretty disk on, what we call it, like where like, if this is us, like this is the plane of the disk. Because that's gonna give us the best. We can't really because if it's only transiting a small part of the star, we're not going to see a very big dip or a very long dip at all. But from based on that dip, like that dip data, those light curves, we can actually try to constrain like the inclination of the orbit, the plane of the orbit, and stuff like that.
That's nice.
Or also the eccentricity of the orbit as well.
That's nice. Anyway, I think you mentioned earlier that you interned at NASA. So what does interning at NASA mean? Or
Yeah.
process or stuff?
Yeah. So I will say, I think I had to be a U.S. citizen, at least for this particular internship. They do take on foreign nationals in some cases, but it's much easier to become an intern if you're a U.S. citizen. So it actually worked out that I talked to the person who then became my boss, my freshman year of college, because he was the former boss of a grad student that I knew at Arizona State College. And he interviewed me, and it kind of the consensus was, come back in a couple years. You don't really know much. So I did. I came back in a couple of years as a junior, and I interviewed with him again. And he's I guess he was impressed enough to let me on the team. And that was the Exoplanet Watch project I was talking about. So yeah, I interned there. I was doing a lot of just software work and looking at these planets in their orbits. And I stayed on for another year. So I did a summer internship that continued into the year, and then I finished up formally last August. But I've still been working with the team, like now.
So what has it been like for you working at NASA? I mean, work wise or culture wise or whatever.
I would say work wise, it's pretty like 9 to 5 normal, you know. But culture wise, it was amazing. Like I got to meet so many people that I wouldn't have met if I had just stayed like in a regular university, astro department setting. I got to meet engineers working on, Mars rovers, Mars sample return, which I won't get into the details of that. That has funding issues, but I also got to meet I got to meet the people who drove the rovers, like Perseverance. So what they would do is they had exact replicas of both Curiosity and Perseverance in what they called the Mars yard. And they would test, if they wanted to, send a command to the rover, they'd first test it on the replicas. If it worked on the replicas, then they would send those commands to the actual rovers. And that was so cool being able to talk to them and meet them. And one of them was actually an exoplanet scientist. So she did her master's doing exoplanet stuff, but then decided that she wanted to shift to engineering and then became a Mars driver, which is really cool.
Wow. Very big shift.
Yeah. And so, as a scientist, I feel like we don't really get to interact with engineers very often. Especially astro people, like unless we are directly involved in the creation of a telescope, we don't talk to engineers. So that was really cool to see what everyone else was up to, and in the passion as well, because you don't go to JPL, because that's where it was, the Jet Propulsion Laboratory. You don't go to JPL for the pay. It's in LA. And there are so many other aerospace companies there that will offer you way more money. So if you're working there, it's because you really want to be there and you believe in the mission and you're really passionate. Not that the other people at aerospace companies aren't passionate, but I think JPLers that are just a different breed. So
That's nice. So your work is, since you're mostly an astrophysics person, it's more about calculation, simulation.
Data analysis and simulation. So there are some people who actually I did do some observing as well. But mostly data analysis. So I work a lot with Bayesian statistics, all that stuff. Some more I find it easier to talk to a machine learning person sometimes than someone who is getting the data straight from a telescope.
My image is that, for example, if you're working in any observatory in general, when you're working as in astronomy, there's a very, very huge amount of data. So how do you deal with such amounts of data?
Well, you sit there for a long time and wait for your code to run.
Then
I mean, maybe you go get lunch and you come back and it's still running. You're like, oh, okay, maybe I'll read a paper or something. or you put it on the supercomputer. Or you put it on the supercomputer.
So in JPL, there's also a supercomputer that's waiting to crunch down the data.
Yes, JPL has supercomputers. I was lucky that my university had a supercomputer as well that I had access to. And I know not everyone has access to that, but I actually prefer work that can be run straight on my laptop because at least I can babysit it and see what it's spitting out.
Oh. So for how about the work that you are currently doing right now? So I heard you're doing some kind of projects or exoplanet analysis.
Yeah. So right now, so I know the underneath says WASP 104P. So that was a project that I did with a class last year, my senior year of undergraduate. So with Exoplanet Watch, it's nicely designed in that it can be used in the classroom. So we collaborated with some robotic telescopes called the Micro Observatory. So these are just 6-inch telescopes that take data every night. And it's waiting for people to analyze that data. So it worked out that a class at Arizona State, where I was doing my undergrad, was offering they were offering a class for students who were online students to get involved in authentic exoplanet research. And so the idea is that we give this class, a set of data from some exoplanet, in this case WASP 104e, and they go through the steps of analyzing the data. Well, first of all, learning what the project is, how to analyze the data, what the data is telling them, and then reducing it, filtering it all out, and at the end of it, writing a paper. And so my role in this was originally I had no role. I didn't know this class was happening when it first started. It was lucky that I interned on the project, and my boss was friends with a professor at my university. And I was like, "Oh, you guys are working on this?" And they basically just asked me "Oh, can you help us interpret our data? We don't really is this weird that what we're seeing or stuff like that?" And so they gave me some of their results and their data, and I ran it through my own analysis tools that I created over the summer. And what we were doing is trying to find, we call them TTV, so transit timing variation. Because with Exoplanet Watch, we don't really have, because this is a 6-inch telescope. This is not that big. So we're not doing any kind of atmospheric characterization or anything. But what we're interested in is the time of the transit, the time of the dip, or we call it mid-transit time. Because The idea is, okay, so let's say so I'm kind of going off on it. I'm kind of all over the place, sorry. So we have a transit, and we're like, cool, an exoplanet's there, cool. But I'm gonna leave it alone for now. I don't really care about it. And then I come back in 5 years, and I'm like, okay, I want to observe this planet again. So maybe when I first studied it, I knew when the planet was going to transit, plus or minus 1 minute. But each time the planet transits, and each time you don't observe it, those uncertainties get bigger and bigger. Mm-hmm. And so maybe now, like way in the future, I know when this planet is going to transit plus or minus 30 minutes or plus or minus an hour. And that wastes a lot of time. So if James Webb, like for example, the James Webb telescope, has to observe a target with plus or minus 1 hour uncertainties, that's wastes a lot of time when it could be looking at other targets. And so the goal of Exoplanet Watch is to basically get those uncertainties down. And keep those, so we need to routinely observe these exoplanets to make sure their uncertainties don't get like super big. So that's the premise of Exoplanet Watch. And so transit timing variations are what I was looking at. Basically, if there's one planet and one star, it should follow a certain Keplerian orbit, and we should be able to calculate exactly when it's going to transit every single time. However, and basically what we do is we observe when the planet transits and when we calculate it to transit based on a Keplerian orbit or a constant orbit. And we create what's called an O minus C plot, observed minus calculated. If everything's according to our calculations, your observed minus calculated should be 0, right? Because your observed should match your calculated. But if that's not the case, if maybe, the planet's not on a Keplerian orbit, you're not going to see a 0. You're going to see maybe, periodic variations or, there's also noise. There's also noise in your observations, which could, make it go away from 0. But what we're doing with these transit timing variations is to see, is there a signal basically in our residuals, in our observed minus calculated? Do we see something like a sinusoid or periodic variation that could indicate that this planet is not just, in a one planet system, like one planet, one star? Maybe there's another planet that we can't see gravitationally tugging on the inside planet, which can be causing it to transit at, a time that we don't, before or after what we expect. So my job in this helping this class was to look for these transit timing variations in their residuals, in their own. A spoiler alert, nothing, which is okay. Which is okay, but I think it's the fact that we did the analysis is what's good.
Interesting. Actually, I find it very confusing how to actually determine if what you're observing. I mean, we've talked about it earlier, how you say that something is an exoplanet, but what if this planet actually, as you said, something is around it, or what if there are other things, or somehow in one observation along its transit, you observe that there's two, I don't know, how do you call it? Target materials or another extra planet that's going with it as you observe. So the amount of dip is suddenly different. So for me, data collection takes a lot of time.
Yeah.
So how long does it take for you to specifically say that this is an exoplanet?
Good question. So there are a lot of planets that are planet candidates. So maybe we've only seen one dip or two dips, or maybe like we thought we saw a dip, but it's not like statistically significant enough. Like it's not enough of a dip to be considered a dip. So those are all planet candidates. We actually, I think the criteria, I think is you have to see 3 periodic dips in order for it to be like, yes, this is a planet. So actually that's another arm of Exoplanet Watch is planet confirmation. And so sometimes there are some telescopes. So there's one called TESS, Transiting Exoplanet Space Satellite, maybe TESS. So TESS surveyed a lot of the sky. Survey satellite, that's what it was. So TESS surveyed a lot of the sky, and so it was able to detect and confirm some planets. But there were some planets that it found that are still candidates. So we still don't know for sure if it's a real planet. And so sometimes there'll be alerts in our Exoplanet Watch Slack, this planet candidate may be transiting tonight. Everyone get out your telescopes and see if you can find it. See if you can get that, get that transit. And sometimes nothing. Sometimes people go out and there's no dip. But sometimes there is. So sometimes you can confirm those planets.
So for when you use, for example, a telescope, is it just focused on one star, or you have image of a bigger space that actually this is the only small portion that where you're observing the dip, or really just focus on that star and then look?
You're taking an image of a part of the sky. And so if I know that there is an exoplanet around this star, I'm going to find that star, but I'm going to have I don't have the ability to get to have just that star in my field of view. And actually, I don't want just that star in my field of view. I want what we call comparison stars in my field of view. So I basically take a bunch of images of the same part of the sky, and I'll be able to identify my host star, and I will also have comparison stars, which I can. The idea is okay, if there is atmospheric turbulence or a cloud that rolls through, whatever effects it has on the host star will also happen to the comparison star. So I basically will know that that was an atmospheric thing, that wasn't the host star going crazy.
So just kind of
calibrate the data. Exactly. They helps calibrate the data.
Nice. Okay.
Yeah. So actually, a lot of mistakes that people make is why don't I see a transit? Oh, when I was doing my analysis, I chose the wrong host star.
Okay. Yeah.
I centered my analysis around the wrong host star, or around the wrong star. So,
how about this other project? It's written here, the SkySurf project.
That was something I was involved with in my freshman year, and I'm really glad I wasn't involved for that long. And I was just a little 18-year-old freshman, so I didn't really do much. But it was the project that introduced me to Linux and how to do command line stuff, what Hubble images look like. So I'm really grateful for that project for kind of letting me in as a freshman and teaching me things. But that project, the basis of it is that most of the photons that the Hubble Space Telescope collects are from our solar system. 95% of the photons that Hubble collects are from our solar system. Obviously, that's not when Hubble is looking into deep space. That's not what we want. And not only that, but a lot of the photons that go into Hubble are not from what we call resolved sources. It's not we see the stars in the sky. Most of the light that goes into Hubble are not from those points in the sky. Mm-hmm. It's from the diffuse light. So SkySurf, it's not, it's using Hubble's entire archive to try to categorize and measure this diffuse light. Basically, the sky surface brightness is what we call it. And so when we want to calculate the brightness of the sky, the diffuse light, because again, when we observe things, you want to, subtract that out. Mm-hmm. And so, and there are also things, the diffuse light, some of it could be from photons that are, scattered by the Earth's atmosphere or re-emitted back from the Earth. It can be from instrument systematics. It can be from like the point spread functions of other objects that are just like leaking into the photos or the images. So we're trying to get like a number to constrain that sky surface brightness.
So the point is to remove my image is, so I'm in optics, so I'm thinking in terms of optics. So you have your subject, but what you're detecting here is completely blurred out because you have an entire area that's diffusing everything. And
Kind of, yeah. I guess.
so
'Cause especially since Hubble's trying to look at stuff that is really faint so far away,
yeah.
we want to get rid of all that excess stuff in the middle.
So
Just want
you're thinking that this entire area is a diffuser of some sort. So you have to, okay, if you find, based on my, as you said, archive from the Hubble, we know that this is what's diffusing the signal. So it's like deconvoluting.
Yeah, I think so. I think that's a good way to put it. Yeah, and we want to measure it
Okay.
because we want to get rid of it. We want to know how much of it to get rid of.
That's nice.
But yeah, so I have some cool friends leading those projects. I don't really know much beyond the introduction to that. But it is a really cool project. I was just the person like downloading the images and like trying to put all the images on a hard drive.
I think it's very interesting. I mean, considering you were still a bachelor at the time, and then you already
I was
introduced to
a
this
freshman. It was like second semester freshman year.
Whoa.
So most professors like they don't give a crap about undergrads.
Yeah.
But this professor at Arizona State, one of the nicest guys I've met, like he wanted undergrads on this project. So his name was Roger Windward. So he's like really big James Webb guy too. But yeah, one of the nicest professors.
Anyway, so now that you're doing your research, is mostly focused on detection of exoplanets. How do you think this would understand? Because I think most people don't, I mean, general public are not really familiar with exoplanets. The only planets we know are the 9.
Yeah.
Is it?
No.
Sorry, Pluto.
Oh no. Well, I will say there's some people hunting for Planet 9 too, which is a whole nother thing.
No, I didn't do it. So anyway, how do you think this would contribute to what we know about astrophysical phenomena, or even how we perceive the universe?
Yeah, so I guess I'll talk about exoplanets generally. So a lot of once I was asked like, oh well, are we studying exoplanets so that one day we can go travel to them? And I was like, that's like the Elon Musk answer. I feel like, I don't. I'd have to talk to some engineers. I don't think we're anywhere near like I don't think we have the ability to travel to other planets outside our solar system. But rather, I'd say that we study exoplanets to understand our own place in this universe and understand the uniqueness of our own solar system, and then eventually also like the uniqueness of life, right? Because the first exoplanets that we were really seriously studying, especially with their atmospheres, were what we call hot Jupiters. So these are Jupiter-sized planets or bigger, orbiting like on the matter of like days around their star. We don't have that kind of planet in our solar system. But that's an interesting question. If we did have a hot Jupiter in our solar system, would we even be here? Like, can other planets exist in the same systems as hot Jupiters? Do hot Jupiters even have like companions with them? Do they have moons? Our Jupiter has moons. Do they have moons? And so so far we haven't really. I don't think we've either found no companions or not many companions to hot Jupiters. But and then another thing is the most common type of planet in our that we found in other systems is something called a super or sub-Neptune. So basically in between the size of Earth and Neptune. If this is the most common planet in our surrounding area, in our local, around our galaxy, why don't we have one? What are they like? Like, how do they form? So there's all these questions about, like, okay, why do we not look like these other systems? Why haven't we found a system that looks like ours yet? Is it because we don't have the precision in our telescopes to look for them yet? Because, if we try to detect Earth like we detect other exoplanets, like with the transit method, there are other methods, but transit is probably the most fruitful. We would have to wait every 365 days to see a transit. Are we going to be staring? Like, how would we know to look every 365 days? And so there are a lot of planets that we probably haven't found yet because they have such long periods. So how would we even find a system like ours? So that's another question. So I would say, yeah, we study exoplanets to understand our place in the galaxy, which is also like life. Can life exist in these other systems? Oh wait, okay, wait, hold on. Another thing. 70 to 75% of the stars in our galaxy are smaller than the sun. So the sun might be like, average size, average age, or whatever, but it's pretty big compared to the other stars in our galaxy. Most of the stars in our galaxy are very cool. We call it red stars, or envelopes is what we call them. With these stars, there are some things. The habitable zone of these stars is much closer into those stars because they're much cooler. So while the habitable zone for us, might be like 365 days of an orbit out, these other stars may have habitable zones around like 10 days. So it only take 10 days for a year. What does that have implications for light? Like, what if the star sends out a stellar flare? Would that kill all light because it's so close to its star? Like, can life even exist around these stars? So I think that's why we study exoplanets.
That's very interesting. I feel like a lot of people doing astronomy research has a more existential question that they're trying to solve.
I hate existential questions. Oh my gosh, like black holes, I hate them. Like, that's scary. It's scary. I don't want to be spaghettified.
But it's actually quite interesting. Like, we are used to where we are in this planet, so it's nice also to know what else is there, or we always think that, are we really alone in this universe? What is the possibility of life?
Yeah, exactly. And I love that question. If you asked me a year ago, I would have told you I didn't care. But recently I've been like, wait, actually that is a cool question. And it is scary. But I think the coolness overcomes the scary.
Actually, we had this guest previously. Her research is also in exoplanets, but her research is on the instrumentation part, like what you put in the telescope. So it's quite interesting. Like, it's meeting.
Yeah, well, I'm gonna tell you, I can't even build like a gingerbread house. So I'm definitely on the theoretical side of it.
So it's quite interesting because I was also asking her, like, how do you know that an exoplanet can support life?
I'm curious as to what she said, because
Actually, she's more on the development of the instrumentation. So
so how do we know an exoplanet can support life? So that first of all, let's assume that life exists like it does on Earth. That's a very big assumption, but let's make that assumption. So we would have to look for an atmosphere, right? We would need to have our best target will be a rocky planet around a sunlight star that has an atmosphere. And that atmosphere, needs to have things like oxygen, methane, carbon dioxide, nitrogen, blah, blah, blah. So one thing that we're doing is we're looking into the atmospheres of planets, and we're trying to find what we call biosignatures. But that doesn't necessarily mean just oxygen, because oxygen can exist on its own inorganically, right? So what we're looking for is molecules or pairs of molecules that could only exist if there was something, maybe biological, pumping, those into the atmosphere.
So like
Yeah.
making the cycles.
Exactly. And sometimes we were basically looking for disequilibrium. Like, these two molecules, they shouldn't exist together. There must be something else supplying, that other molecule. Because like on their own, they shouldn't exist at these levels together. So that's one way we can look for life. But again, that is also very difficult. To probe. It's much easier to observe Jupiter-sized planets than Earth-like planets. And we still haven't really pinned down, we haven't really got good constraints on the atmosphere of an Earth, like a rocky Earth-like planet yet. We've had non-detections. We found rocky planets that have no atmospheres. But we've also found rocky planets where there could either be no atmosphere or a really thick atmosphere. Sometimes it's really hard to tell the difference between no atmosphere and thick atmosphere, funnily enough. But again, we're assuming that life is like life on
Same as Earth.
Yeah. Is it good to make that assumption? Maybe. We're the only data point we have for life in the universe, right? So it would make sense that we're going off of what we know, but there could very well be, silicon-based life or life that doesn't look like what we expect it to look like. But how do we know what we don't know? How do we know to look for something that we don't know exists? And it's going to come down to also like we need to get money from the government to do this stuff. So if we tell the government, I want to look for life, I have no idea what I'm looking for, they're going to say, you're stupid. No, we're both not give you money. So it's easier to make a case of like, okay, government, these are the exact things I'm looking for. So yeah.
But I think it's a good start though. Like, to know things that we do not know, we start with what we know.
Exactly. And we're gonna make like James Webb, it launched like 2021, Christmas of 2021. There's still so much more science to do with it. We're gonna discover a lot more. It's gonna, I wouldn't say like, I could say revolutionize our understanding. Because there are a lot of things that we theorized, but we haven't been able to check. We haven't been able to observe yet. So James Webb will give us that ability to get down to precisions where we can be like, oh, wait, this is actually happening.
But so how far do you think has exoplanet research gone? Like how far or how much more?
Yeah. So this field is less than 30 years old. And if you I think Einstein published his thing on special relativity in like 1905 or around that time. And people have been studying astronomy for ages. The first exoplanet around a sun-like star was found in 1995. Oh. So there are a lot of astronomers that are older than the field of exoplanets, but that have been in the game longer than the field has existed. And the fact, we've come a long way from then, and very quickly as well, right?
Yeah, that's true.
And we've done a lot of exoplanet studies with Hubble. Hubble was not even designed to study exoplanets. Hubble launched before the first exoplanet was found. So we've gone from, in 1995, finding an exoplanet to now probing the atmospheres of Earth-like planets. Which I think, and we do low resolution, we do high resolution. We do stuff from the ground as well. We've taken pictures of exoplanets. like actual pictures. So yeah, the field thought kind of came really far, and in the future, one of the things that came out of the Astro 2020 decadal. So basically, every 10 years, astronomers come together and be like, okay, what's important to us? And in 2020, they released the decadal where they said, what's important to us is taking a picture of an Earth-like planet around a sun-like star.
Mm-hmm.
So we have James Webb. After James Webb, we have, some other telescopes. Well, what we want to work up to is we're calling it the Habitable Worlds Observatory. And so this is the observatory that we want to use to take an Earth-like or a picture of an Earth-like planet around a sun-like star. We're having trouble with the technology. Like, we're still developing the technology in order to probe down to these differences. Because what you're trying to do is you have a really, really bright star and then like a little planet that may not be emitting that much light. How can you block out enough of the starlight in order to see that planet from so far away?
Yeah.
Like, I mean, and to put it in perspective, like the outer solar system planets, like our picture that we had of Pluto was like super, super duper, like maybe like, I don't know, about 5 pixels. The super duper pixel. We only have a good picture of it now because Voyager, went out there and photographed it and did a flyby. So that imaging, it's called high contrast imaging. And we trying to block out the star's light in order to get that image of the planet.
So currently, what you're trying to say is the main challenge is mostly on the detection side, so the instrumentation.
Yeah, there's a lot of, well, not just instrumentation. There are a lot of instrumentation challenges. But also like fun, we have a lot of ideas. We just have to get the funding for it. But there's a lot of issues also on the data analysis side of things, the interpretation side of things. Because ultimately, we're looking at a bunch of bumps and wiggles and we want to match those. Like if we're talking about atmospheres, we have a bunch of bumps and wiggles, and we're trying to match those up to molecules that could be in those atmospheres. But remember how I said before, like no atmosphere can look a lot like a thick atmosphere?
Mm-hmm.
That's because of like clouds. Clouds are the number one enemy in astronomy. More so for exoplanet scientists. So obviously if you try to, if you're on the ground and you try to look at that star and there's a cloud in front of it, you're like, oh man, cloud it out. With what happens with exoplanets is if a planet has clouds, like heavy, big clouds in its atmosphere, all of the what's the word the spectrum of the planet. So like basically, the signature of what's in the atmosphere, that's all muted. The cloud has the effect of like muting the atmosphere and the signatures of the molecules in the atmosphere. And so when you don't see those bumps and wiggles, you might see, oh, well, there's no atmosphere at all. And so that's how a thick atmosphere can look a lot like no atmosphere when there are lots of clouds. And, it would be nice. A lot of papers very early said, oh, we're assuming no clouds. Actually, some of the work I did with brown dwarfs, it was in a very specific subset of brown dwarfs because we could assume no clouds because we didn't want to mess with clouds because they're hard to deal with. But when obviously planets with atmospheres have clouds, right? I mean, Earth, you look up and there's clouds. Venus, clouds. Jupiter, clouds. So we have to deal with clouds and we have to learn how to model those clouds and how to differentiate between, a cloudy atmosphere and no atmosphere. And then that goes to instruments, right? Like we need the precision to really, if there are clouds, to still get those bumps and wiggles so that we can fit that with a model.
So for the work that you're currently doing for your projects, your main challenge is also in the data interpretation mostly.
Oh yeah, so I guess I should describe the project I'm currently doing. I didn't even do that yet.
Also,
yeah. So it's still right now I'm still working with Exoplanet Watch team. and we're doing a study on the planet Qatar 1b. There's nothing I would say particularly interesting about this planet, as opposed to other planets. However, we have a lot of transit data on it, a lot of it, both from amateurs and from professionals. And so what I am trying to do, and so again, no atmosphere stuff. This is just looking at the timings of the transits in those observed minus calculated plots. What I'm trying to show, not necessarily that there are TTVs or like there's, there's another planet in the system, but what I'm trying to show is that amateur data is just as useful as professional data. Because Exoplanet Watch, it's a community of amateur astronomers, right? And I feel like a lot of professional astronomers are quick to dismiss amateurs. Like, oh, well, how could you possibly get good data? Like, how would how could you possibly have data that we can trust, right? You're not trained. Okay, but to be fair, like, in college, they don't train you how to use, collect data from a telescope and analyze it. Funnily enough, I never got trained to do that in the classroom. But amateur data can, I have some plots somewhere, like with light curves, 2 light curves. One is professional, one is amateur. The amateur one looks more precise than the professional one. And anyone, as long as you follow the proper procedures, can produce good data. And so, but the truth is that amateur data does have more scatter in it. There is more noise, but as long as you account for that in your error bars, as long as you basically account for your error accordingly, the data is still useful. And so, the idea is okay, it's better to use amateur and professional data combined than, no amateur at all. And even if you just analyze the amateur data by itself, it doesn't give you wildly different results from the, professional data by itself. So maybe the main challenge for that is getting over prejudice maybe not prejudice, but the ideas of the professional astronomers that amateurs can't do anything right. They always make crazy wild claims.
So for your work now you're working in Ateneo. Is it still in collaboration with your previous work?
So technically, under my grant, no. So that is a completely separate project. I'm just kind of doing it on the side. So what I'm doing here in the Philippines is, well, originally I was going to actually create and teach a class, because my rationale for being here is the Philippines doesn't really have that much astronomy going on. Maybe I can come in and create a class, or maybe even using Exoplanet Watch that will help people get authentic astronomy research experience, or maybe I can create a class that is like astronomy labs, like intro astronomy labs. But what I realized since I've been here, classes aren't what the Philippines needs, or the Philippines astro community needs. But look, class material, information about astronomy, you can get online, right? So what I kind of shifted my project. Also, I had some crises of what am I even doing here? Especially because the Philippines right now is more focused on space stuff. I think there's a common misconception that space and astronomy are the same thing. Or space and astrophysics. I mean, it would make sense, right? That space and astrophysics are the same thing, but they're not at all. So astrophysics is academic research and study of stuff. It could be planets, stuff outside our solar system. Space, you're talking more business, satellites, commercialization of space, telecommunications, stuff like that. So there's no real, maybe you have conversations about astronomers might get mad that this, all these Starlink satellites are contaminating my images. But that's pretty much it. So I'm reconciling like, okay, if the Philippines right now is pushing for space, which is profitable, astrophysics is not profitable, right? That's all government funded. Like, what if, what am I here to do? And also, like, is it right to be pushing, telling people, yeah, you should totally become an astrophysicist when there are really no opportunities to do that in the country. So I've been grappling with that a little. So I kind of shifted my project more into like, at the end of this, like writing a report on, okay, what is working in the Philippines? What is not working? What do I like? What have I seen? What have I observed? And what areas need more help? What areas are we doing well in? Stuff like that. And I think so. Just beginning, I haven't really put it out in the world yet what my observations are, but I see a lot of different groups, different people doing their best to this is a project I put together, and they all have good intentions. Like, this is to help people get more interested in astronomy, but the parts aren't really working together. Like, the individual initiatives aren't really working together. I mean, they're all good, but they're not.
There's no cohesion.
Yeah, there's no cohesion, and it honestly, there could be that like trying to optimize one area of the space environment will hurt you in the long run. For example, right now we have a lot of people interested in astro. We do have a lot of astro outreach. There are some universities that offer an astronomy degree, but there are no opportunities once for professional astronomy.
Yeah.
There aren't many PhD opportunities in the country. Like maybe UPD, but like, again, not everyone is going to be able to do that. Work with that one. Raina Reyes at UPD or something.
Yeah.
So we're still lacking professional opportunities. And but that's the thing. Astro was government funded. So at the end of the day, I'm like, well, crap, we need government funding. The government needs to commit to funding, these positions.
That's true.
Yeah.
But do you think in the setting of the Philippines, if we want to enhance the research in astronomy and astrophysics in general, I think for me personally, it would be helpful that if we have external collaborations or start with an interdisciplinary approach. But how do you think about this?
Yeah, no, absolutely. I mean, most collaborations in astronomy, I would say, are international. And it's really hard to do astronomy by yourself. So it would be great that if we could collaborate with more people outside. Again, we also need we need more astronomers like in the country as well for that to happen. For this collaborations to happen. Interdisciplinary too. So I will say this one thing about astro. It is probably, out of most of the sciences, it is the least costly, because all your funding for the most part is the researcher versus, chemistry. You have to fund a lab, you have to fund you have test tubes, Bunsen burners. I don't know what chemists use, but there's so much equipment that comes with it. Versus an astronomer, a lot of the data that we use is publicly available. A lot of James Webb data, publicly available. So you don't need, I mean, of course it'd be nice to have a telescope in the country, but you don't need, yeah, right. But it's very low cost and easy to get into. And so, and again, there's so many, astro is physics. It's just physics applied outside of, the Earth. So, so, I mean, and also like there's chemistry involved. There's a lot of like lab-based experiments, especially with exoplanets, like, testing chemistries in a lab so that we can then use that information in our like model codes. That's an area where you can get into astrophysics. I mean, astrobiology, right? There's the biology component, so studying extremophiles, or and also like programming, coding, machine learning, all that stuff.
That's like, that's where you start.
Yeah. I mean, honestly, that would even be easier, right? There's so many astronomers out there that need to optimize their code. In a lot of like exoplanets, it's very data driven, and it relies on people knowing how to code, knowing Bayesian statistics, knowing, we're getting more to the machine learning area as well. So yeah, there's so many avenues in which to get involved in astrophysics. I think honestly, like knowing facts about astro is like at the bottom of the list of things that you need to have, right?
Yeah. So it's mostly about just investing in manpower.
Yeah, no, investing in people,
In people, yes. But I think in the Philippine setting, it's quite difficult to pursue a career in astronomy and astrophysics because of the future of it. Like if you have a degree, if you got a PhD in astrophysics, for example, what is next?
Great question. I don't know. I mean, like, even for me, right? Like,
actually, even for me.
yeah. I mean, so I know people. Yeah, so it's especially when even like your undergraduate education is being funded by your parents. It's hard to justify because I mean, okay, what are you going to do with an astro degree or even a physics degree, right? Like before when I was like figuring out like that I actually wanted to come here to the Philippines, my mom told me, "Oh yeah, physics that's like that's a rich kid degree. Like that's something only a rich kid could do because there's no guarantee of like how it's gonna make money."
That's true.
Yeah, and so like if you have the money to go to college, if you can afford to go to college, you're studying nursing,
Yeah,
that lets you know that's gonna make money. So yeah, exactly. Actually, if you're so interested in science, why don't you go be a doctor? Why don't you go be an engineer?
That's true.
Yeah. So what was the question again?
What's next?
Yeah, what's next? Yeah. So I mean, with an astro PhD, with an astro degree, you get a lot of. It's very interdisciplinary. You get a lot of things in your education. So a lot of people end up in like data science or software engineering. Some, if you're lucky, you're able to become a professor and continue doing your research. I know people who shift to like climate science jobs as well. People go to public policy. One of my friends is getting her PhD in astrophysics and plans to go into policy, space policy. So there. I think people don't realize how many options they have. Also, because you can do whatever you want. Like I could get my PhD in astrophysics and go try to pursue art full time. I mean, I could, but it gives you a lot of technical skills. So and a lot of that is surrounding coding. So there are a lot of options with astro.
I think not just in astro in general. I think, for example, for me, I graduated physics. And people assume, okay, you graduate physics, maybe you're going to be a teacher. But I think the common misconception is that when you say you graduated this course, this will just be the track that you're pursuing.
Exactly, yeah.
But the thing is, it's nice that we gained a lot of technical skills along the way. So it's not just about saying, I'm an astrophysicist, I'm a physicist or something. But when you say I'm an astrophysicist, I have a good knowledge of how to code. I can pursue data science if I want to, or so on and so on, different kinds of fields in general.
And specifically a PhD, like how to problem solve.
It's more critical thinking.
Yeah, how to think independently.
That's
which maybe not all employers want you to be able to think independently, but I think it's a good skill.
Yes, it is. I think so too. So, do you think now, in the current setting, maybe for in the Philippines or maybe even outside the Philippines, do you think astrophysics or astronomy is something that students would want to pursue? Is it is the community getting bigger and bigger? More students coming in?
Yeah. Oh yeah. Like, especially now with social media, we're able to like share, there are some people who are like space influencers and they like share facts about space on TikTok or whatever. Oh yeah, it's growing really fast. There are so many students that are interested in space, and actually that shows in undergraduate enrollment as well. So like for schools that offer astrophysics undergrad degrees, like Arizona State does, there are a lot more in physics as well. There are a lot more students enrolling in physics, enrolling in astrophysics. And honestly, it's a lot harder to get into grad school now, like get into PhD programs because there are so many students interested in these programs.
Nice. So for these kinds of people, maybe just to also conclude this discussion, what advice would you give to our listeners that actually want to pursue or maybe just are purely interested in astronomy and astrophysics?
Um, I'm not going to sugarcoat it, because it is like, I mean, I said before, getting in, it's very difficult to get into astro professionally. It's very easy to be interested in it. There's so much information online to feed your interest, but actually doing it in school and as a career is a lot harder. But not, I mean, of course, the material itself is difficult, but just because the opportunities are so limited. But that's not to say you shouldn't. Well, you absolutely should. It's so rewarding and it's so fun. But I will say you have to truly believe in your potential to succeed. And not in your potential to succeed, but rather your potential to overcome challenges. Because there will be a lot of challenges. I know people who, their dreams from an astrophysicist, they were rejected from graduate, like maybe they got into one graduate school out of 30 over the course of 2 application cycles. Yeah, so it's really different. You have to be resilient, and you have to be also like smart about what you do, like in your choices. And I guess another thing I would say is you learn to become an astrophysicist outside the classroom. It is not by sitting in a classroom and learning quantum physics that you become an astrophysicist. All of, I think all of the experience, all the skills that I use now as an astrophysicist in my research was learned outside the classroom. And that was through me, like, you have to like really go for those opportunities, right? Or if there are no opportunities, make those opportunities for yourself. So Exoplanet Watch is free to join. And it teaches you, and you can get really involved and learn how to do research with it. So I will say that I will plug Exoplanet Watch. If you just Google Exoplanet Watch, it'll appear in the search. But yeah, you really have to go for it outside the classroom. Find mentors. Those can be like if you have, instructors, that's great. Older peers, people online. I mean, do well in your coursework too, I guess. Learn how to code. Learning how to code. Astronomers, that's all they do. Learning how to code, trying to find different projects. Showing that you are really passionate about this. Like, so doing projects that show you really passionate about this as well. But yeah, I think that's what I have to say. So be resilient and, don't stop trying.
Believe in your passion.
Yeah, believe in your passion. And know that there will be a lot of setbacks.
Sure.
But if this is your passion, keep going. Like the power of self, and the power of self-belief is crazy, right? Or to put it in Gen Z terms, Delulu is the Salulu, is what kids say nowadays. No. So you have to really truly believe in yourself.
Yeah, that's true.
That's
Calculate yourself.
yeah. Exactly.
Repeat until true.
Yeah, exactly.
Okay, so anyway, that was a very interesting talk. So I learned a lot of things today.
Yeah, I was all over the place. I'm sorry. I just recovered from COVID, so I have COVID brain. And let me tell you that I feel like I'm on drugs.
I mean, that's you speaking on COVID brain. What about without COVID? Right?
I don't remember who I am.
Yeah, anyway, thank you for joining us today in this episode. I still have a lot of questions, but there's so much time already. Anyway, thank you for joining us, and thank you, Easy, for joining us today. And
Thank you for having me.
everyone.
Yeah, thank you for letting me ramble for an hour and 6 minutes.
Okay, so thank you everyone, and stay tuned for the next episode.
So maraming salamat sa panonood ng ating bagong episode at kung nagustuhan nyo yung ating video, huwag nyong kalimutang i-like na yan at click na yan para masuportahan ang ating channel. Maaari nyo rin panoorin ang iba pa nating episodes dito.